We restart, okay, for the third lecture. So today we will hopefully reap the benefits of all the work we did during the two first lectures. So this should be more relaxed from the point of view of calculations or whatever. So I remind you what we had. We had this dictionary which was rewriting essentially bosonic and later fermionic and so on problems in terms of collective variables. And with that, we have a nice expression of the density of the single particle operator. And the remarkable thing was that we could rewrite the Hamiltonian of an interacting bosonic field at the moment of an interacting single particle bosonic field as, oops, I don't know why the dot doesn't appear, as a quadratic and essentially harmonic oscillator Hamiltonian. And at the end, we had only two parameters, so the coefficient of these two terms, which can be rewritten as a velocity, which correspond to sound waves, and a dimensionless parameter. And because we have now a quadratic Hamiltonian, we can compute all the correlations, essentially. And we worked out, so essentially, perturbatively, we found that the velocity is proportional to square root of u. The parameter k is roughly 1 over square root of u. So k is very large for small interaction, very small for large interaction to be requalified. And with this Hamiltonian, we computed the correlation functions. And we found that the density correlation function essentially varies as a uniform term which decays as 1 over x squared, essentially, and then oscillating term whose amplitude decays as a power law whose exponent is controlled by this parameter k. And there is an oscillation at 2 pi rho 0, 4 pi rho 0, 6 pi rho 0, and so on and so forth. And this is what you would expect in a crystal. But of course, because of the quantum fluctuation, the crystal is destroyed, and therefore we expect the amplitude to decrease with space and time. We also commented briefly on the fact that because we have low energy mode, power law decay, around q equals 0, q equal 2 pi rho 0, 4 pi rho 0, we can expect a nice mode here when I do the Fourier transform at omega equal uq, but then I can expect a continuum of excitation around 2 pi rho 0, 4 pi rho 0, and so on, that will touch, of course, energy 0, because if you had a gap here, you would not expect a power law decay of the correlation. You would expect a much faster decay, because you cannot excite things, so you would expect exponential decay of the correlations. We also computed the single particle correlation in average first, and we find that contrarily to what happens in higher dimension, the average of psi of x is 0, so there is no true superfluid or whatever you want to call it. Let's say there is no ordered state. You don't get a finite order parameter which is normally associated with a superfluid. And this is because in 1D you cannot break the continuous symmetry which is associated with the phase of the wave function. But in the same way, the psi dagger, the single particle correlation function, is decaying as a power law with a gain and exponent which is controlled uniquely by the parameter big K, the Tomonaga-Luttinger liquid parameter. So I would say at small interaction, K is large, so you would say the slowest decaying function is the superfluid one, is the single particle one. So probably my system resembles more a superfluid than a crystal. Of course, if K could become very small, which at least naively would just correspond to large interactions, then you would expect that the system looks more like a crystal than a superfluid, but actually you get power law decay both in the superfluid order and in the crystalline order. Okay, so this is what we established. We also showed that the momentum distribution has a singularity, a power law singularity now, and not a delta function singularity at q equals 0. And we sort of discussed very briefly whether these results are correct, incorrect, just because we threw away a lot of terms in the Hamiltonian. And again, the proposal or the idea is that this quadratic Hamiltonian is actually the fixed point in a renormalization procedure where you would say I eliminate little by little the high energy degrees of freedom, and it's the fixed point which corresponds to the low energy properties of any, okay, not any, but many one-dimensional interacting problems, which means that A, what we did is perfectly okay, we can use it, and B, there is a catch, and the catch is that because there is all this renormalization when you eliminate the high energy degree of freedom, the perturbative values that I showed you for the parameter u, the velocity, and k, are most likely not correct, or at least not precise. They might be precise when u is small, because all these higher terms, they become, no problem, they become smaller and smaller, but they will certainly be very wrong if u equal 10 million. You might even, a priori, initially wonder whether I should discard them at all, and so Haldane tells you, yes, you can discard them, but you have to renormalize the value of u and k. And then, how can you determine these parameters? Well, to determine these parameters, there is a very simple trick, because they control the whole low-energy physics. You should just, if you have your favorite microscopic model, Liebling-Lininger, bosons on the lattice, it doesn't matter, and you know how to solve it either analytically with Bethe-Ansatz or numerically with whatever is your favorite method. I won't talk about numerical method. You got a talk last week by Frank Verstraete on matrix product states. So there is a method which is known as density matrix renormalization group that was invented by Steve White and then perfected mostly in 2005 and later by Steve White, Uli Scholveg's group, Corinna Collatz. Well, there are many people, Adrienne Fenguin, there are many people involved in this to not only compute equal time correlation in the ground state, but now to compute correlation as a function of time and at finite temperature. So it's an extremely powerful method, but it's not the only one. You can do exact diagonalization. You can do quantum Monte Carlo. So whatever works. The point is that using this method, either Bethe-Ansatz or these numerical methods, you can simply compute quantities which are easy to compute from the numerics, namely usually thermodynamic quantities. And I just mentioned a few. Specific heat is dependent on 1 over u. It's proportional to temperature, but inversely proportional to u. The finite size dependence of the energy is proportional to u. The response to a twist in a boundary condition gives you the product u times k. The compressibility of the system gives you u over k. So you can do whatever you want. You can even, from the MRG, measure the short distance decay of correlation function and fit the exponent. And actually, this is what practically people do. They take for the MRG, because of the fixed boundary condition, it's extremely inconvenient to try to do a twist of boundary conditions. You cannot do it. So what people usually do, they measure the compressibility, which is super easy. You add one particle, you remove one particle, and you compare the difference of energies with this. I won't go in details. And if you want to get the exponent, so it gives you u over k. And if you want to get k, you just take an equal time correlation function, and you just fit the exponent at reasonably short distance. And then you inject in the field theory, and you can compute the finite temperature, finite time, and so on. Okay. So I just briefly mentioned at the end of the previous talk that, of course, in the calculation from the field theory, the amplitudes are non-universal. They depend on the cutoff. They are, arbitrary because the cutoff is arbitrary in the theory, or at least extremely ill-defined. And the point is that, again, you can play the same game. If you can compute this correlation function at equal time, for example, as a function of space, which is usually easier, for a given microscopic model, either by Bethe-Ansatz or numerically, you can fit the decay of this correlation function, the exact correlation function, and extract the amplitude. And then it's a simple matter to make the connection with the amplitude you would get in the field theory for a given cutoff. So you can even determine quantitatively, either numerically or from Bethe-Ansatz, the amplitude. Yeah, by the way, I see if you want to know why I have a coin in my left hand, ask me during the discussion session. You can also ask me why I have a deck of cards in my back pocket, but that's a totally different issue. Okay, so we'll talk about this this afternoon. The This is extremely important because once you fix the amplitudes, you know the exponent. It means you essentially have the exact or practically exact correlation function. But you can have it by doing a calculation where you only get either thermodynamic or equal time correlation, which is much more easy. Okay? So let me show you a couple of examples. Because after all, you could ask whether what I'm telling you is the truth or whether I'm smoking you out by telling lies. So first, let's look at the density correlation function. Yeah? Sure. Yeah.
In many reviews, they are actually quoted already in the optimization identity. So in the operator mapping, you already say that psi is proportional to some sum of v with each harmonic that is becoming with a non-universal constant.
Yes.
How does that fit into?
So, you know, there are many ways you can do this. Either you say, oh, I have, for example, psi, which is a exponential of I theta, but I don't really know what a is. It's not really square root of rho 0. Yeah. It's non-universal. Then you will write that when you write psi dagger, this is a square times whatever is the behavior of this correlation, which could be alpha over r to power 1 over 2k. But you see immediately that because alpha is the cutoff I've put in my ultraviolet cutoff, this amplitude has to depend on alpha as well. Because the microscopic model, if I take Liebling model, it has no ultraviolet cutoff. It's totally defined. So in order to compensate the alpha which appears here, there must be a dependence in alpha in the amplitude, which will ensure that at the end, I only get something which depends on the physical parameters of the model, which is, let's say, the density, the mass, the interaction strength, and whatever. This alpha, I fix. And I could put an exponential cutoff, I could put a box cutoff, I could put a Bessel function cutoff. So clearly this amplitude is not just a fixed number, but when I fix the cutoff procedure of the field theory, the amplitude is now fixed by this for a given microscopic model. But if I change the microscopic model, I change also the amplitude.
So for a given microscopic model, your bosonization identity, both for density and psi, would basically come with a consistent set of the...
So it's not amplitudes that you get at the level of the operator, it's amplitude you get at the level of the correlation functions. Because you could say that this correlation function gets renormalized also by all the terms you've thrown away in the Hamiltonian. So rather than define the amplitudes, that's why I didn't want to spend a lot of time defining the amplitudes at the level of the operator. I prefer to define the amplitudes for the correlations. Because there, it's a very well-defined physical observable, and you can compute it in the exact model, or you can compute it in the field theory. This is a very good question. We had actually yesterday this discussion with Jérôme and Fabian on whether there could be some magic relation between various amplitudes. And the answer is, at least for me, I don't know. Fabian was much more negative, said no. But the net result at the end of the day, it's extremely unlikely, I would say, based on my own opinion. But in any case, this relation, if it exists, is super complicated. And to the best of my knowledge, nobody has unraveled such a relation. So for a given amplitude, there are exact formulas, for example, by Lukyanov and Zamolodchikov for some models. As I said, now it's routine to, not routine, but it's relatively easy to compute them numerically. And so it's not an issue to have the amplitudes. Whether one can find a more systematic relation, that's an open question, I would say. Okay? So let me show you first something on the correlation function. So I showed you this correlation function. And again, the Fourier transform of this, the imaginary part of the retarded correlation function should be something like this. So this is the prediction of the Tomonaga-Luttiger liquid. So let's compare with something which has been computed. So let me show you, remind you what I was telling before, if this thing wants to start. So, okay, here are the correlation functions that I already gave you. So, by the way, I transmitted both the transcript of the session 1 and 2 which now should be uploaded on the web. I also gave you a copy of the slide up to section 1 and 2, and I also added the chapter 3 of my book in 1D, which will give you all the details of the calculation with hopefully more or less all the prefactors correct and whatever. There is on the website of the group a page with the mistakes which have already been spotted. So if you say, I don't find the right factor of 2, have a look first on this page to see if it's already there. And if it's not there, send me an email because I will add it on the page. So, okay. So this is the correlation functions. This is what we were discussing before, that at 1/2 the thing goes essentially from, let's say, superfluid-like to crystal-like. Here is an exact calculation for the Lieb-Linear model done by the group of Jean-Sébastien Coe of exactly the Fourier transform, the imaginary part of the retarded Fourier transform of the density correlation function as a function. So this is as a function of momentum, energy, Kf, what is called Kf here is pi rho 0. Why it's called Kf, we'll come to that in a second. And gamma is the strength of the repulsion. So this is a very weakly repulsive gas. This is a more strongly repulsive gas, and so on and so forth. So if you see this thing, you would say, oh, this, what I said with Luttinger liquid is wrong. I don't see a continuum here. There is nothing here, but you see the Bogolyubov spectrum-like mode. So you see the Q equals 0 mode that we were discussing, the fact that you get this linear part followed by the quadratic part. So you see it very clearly. Then you increase the repulsion, and actually what you start seeing is that this is not a well-defined mode. It's not a single line, if you want, but it's something which has a width, which has some spectral weight which is there. So, and when the interaction becomes very large, now you start seeing the spectral weight, and you see that there is indeed the part at around the straight line here, and then there is indeed the continuum of excitation, which is around 2 pi rho 0. Actually, this continuum is there all the place. It's just incredibly weak if the repulsion is small, because the amplitude of the corresponding term is super small. So from there, I could also extract, of course, the amplitude of the term, not just the power law decay. The power law changes because gamma, the Luttinger liquid exponent changes, but also the amplitudes depend, of course, on the interaction. Okay? So this is a very, very beautiful agreement between a full exact solution, this is T equals 0, of course, 0 temperature, and the Tomonaga-Luttinger liquid prediction. Yeah.
What happens then at K over Kf equals 2? So do we see a repetition of the spectrum then, or of the line, the mode line?
No, so K over Kf equal 2 here in these notations means Q equal 2 pi rho 0. Okay, so what you see is exactly what I said, that you get a cone-like continuum, which is touching the point at 2 pi rho 0, and this is the signature that at this value of Q, there will be massless modes. There will be low energy mode, because you have a power law decay in real time. Okay? Whether you should see something at 4, you don't see something, will depend on the amplitude at Q at 4 pi rho 0. If this amplitude is magically 0, you will never see something at 4. If this amplitude is non-zero, so here the fact that you don't see something at 4 means either the signal is too faint, and maybe going to gamma equal 200 will make it appear, or the amplitude at 4 is 0. And that's the second point, which is correct, that particular case. Okay? Yeah. Exactly. So, but you have to worry, you have to see in which units this is done. Kf square is a very high energy. And you're absolutely correct. The region in which the Luttinger liquid theory works is the size of the dot here on the horizontal axis. If I try to go here, I am at energies which are much larger than the chemical potential for the bosons. So I am way above the cutoff that I put, which means I'm looking at properties actually at extremely short distance or extremely short time. and then the field theory is completely bananas. But, you know, if I take, for example, standard numbers in, let's say, solids, this energy, kF square, would be typically of the order of 1 electron volt, 10,000 Kelvin. So being there might not be a problem at all for practical systems. So this will depend on the system you look at. We will see examples later. If I look typically at an electronic system, this scale is 10,000 Kelvin. So I do an experiment at 1 Kelvin, I am within the Luttinger liquid, no problem. If I look at a typical spin chain, we'll come back to this, the exchange is 1,000 Kelvin. So again, if I do measure something at 1 Kelvin, I'm fine. But now there are spin systems for which the exchange is 10 Kelvin. And there, I need more than the field theory. And that's why it's important, again, to have the three methods which are able to work together, because this part of the spectrum, you will never get out of the field theory. I mean, this part here, you will never get out of the field theory. As you said, the field theory is working here and here in a small, so let's say, I don't know, omega over kF square equal 0.1, something like this, and then you're perfectly happy. Okay? So this is important to keep these limitations in place and in mind. Okay, so now let's go to the little exercise on an example where I don't want to work of calculation of K and U for the Lieb-Lininger. Okay. So, of course, I can do numerics, and the curves are known, and you can find them in the Review of Modern Physics paper that I gave at the beginning. But let's say I don't want to work very hard, I'm lazy, and I would like to know what are the Luttinger liquid parameter when the repulsion, U, is infinite between the bosons. So that was the exercise I gave you. So now I want to use the field theory for the infinitely repulsive, sometimes also called hardcore limit of the 1D bosons with a delta function interaction. So I have 1D bosons, they repel with a strength which is infinite, which means I have really no possibility to put two bosons at the same point in space. It's really out of the sky. Okay. Can I get my Luttinger liquid parameters for free for this limit? Meaning without having a supercomputer doing DMRG, doing Bethe-Ansatz, reading Elliott-Lieb's papers and things like this. So how would you do it? What would be the trick? Yeah, so it sounds, I have particles who don't see each other if they are not at the same point, and we can never be at the same point. So it would be super convenient to say, haha, I know such particle, it's spinless fermions. Spinless fermions, if you put two particles at the same point, the wave function is totally anti-symmetric, so the wave function has a zero. Actually, it's not exactly correct, in the sense that if I plot the wave function, let's say, where I've fixed the position of all the bosons, and now I plot it as a function of the coordinate xn of the last boson, the wave function has to be totally symmetric for bosons. A wave function of fermions has to be totally anti-symmetric. So my wave function of bosons, it should do something like this. It has a 0, then another 0 at position x1, at position x2, blah, blah, blah. But then it's symmetric. So if my particle, my supplementary particle is here or here, it should be the same wave function. If I had fermions, well, it would not be like this. If I can reach my menu here, that would be nice. Voila. If I had fermions, I would have something like this. The wave function would be totally anti-symmetric. So yes, I could say that particles with an infinite repulsion which are bosonic, they are kind of spinless fermions, but it's wrong for their wave function. But if I only look at things which are square of the wave function, I don't care. So in other words, yes, I can say that my system of bosons, let's say hardcore, is like a system of free fermions. And that's fantastic because I know how to solve free spinless fermions. But Achtung, the wave function of bosons is of course completely different from the wave function of the fermions. So I cannot, for example, compute the single particle correlation function by saying, haha, it's the single particle correlation of free fermions. Well, you immediately see it's nonsense. Function of free fermion has a singularity at kf. The function of bosons has a singularity at q equals 0. I mean, clearly it doesn't match. But I can say that the density, for example, of the bosons is actually exactly equal to the density of fermions, or the current of bosons is the same than the current of fermions, because all these things only depend on the square of the wave function, so I don't care. And now, how can I get my Luttinger parameters? Well, that's very easy. I'll identify the correlation functions of the density with the ones of free fermions. So if I have free fermions, I don't need to do a big calculation. I have now my parabola, k square, over 2m. I have a Fermi energy, EF. I have, of course, kf here, minus kf here, plus kf here. All these states are filled. And now, if I look at the density, I let you do it as an exercise. It's something you can find in all solid-state physics book. What is the density-density correlation of free fermions? You will find that the density-density correlation of free fermions, it has a part that decays as 1 over x squared, and it has a part that oscillates with 2kf, and which also decays as 1 over x squared. It's really straightforward to do the calculation. If you want, take it as an exercise. If you have problems to do that, come to see me. We can do it. But it's very simple calculation. In other words, it's just saying that the low energy modes for fermions, they can be because you take something here and you put it on the same side of the Fermi point. These are the excitation that are here. But I could also do a very low energy excitation by taking something which is here and promoting it, but on the other side of the Fermi surface, then I exchange a momentum to kf. So this will oscillate with momentum to k. Okay? So if I am doing this thing, which again for free fermion is an exercise you could do in a master or even a third-year bachelor course, then you will find that this is the correlation function that you get for your free fermions. But I know the field theory response for the Luttinger liquid in general. I know that this is, whatever, 1 over x squared. Okay, I could identify the amplitudes here, but I have much more simple. I have here a cosine 2 pi rho 0 x times 1 over x to power 1 over 2k. To power 2k. And now you see that I can do straightforwardly the identification. 2kf is 2 pi rho 0. That's a trivial statement. It's just fix the number of particles. But I have also k equal 1. And the velocity is just the Fermi velocity. It's the derivative. So u is just kf over m. It's the derivative of the energy at kf. Okay? So for the Tonks limit, it's called the Tonks-Girardot gas. Or limit, if you want. You see that indeed the thing is mappable onto free fermions, and Jérôme will elaborate much more on that, in particular in a trap, where it becomes highly non-trivial. You see two things. You see that now you get the density-density correlation for free. That's why I could tell you there is no 4kf. Because at infinite repulsion, I know that there is no 4kf. So the amplitude of the 4kF oscillation is 0 when u tends to infinity. Of course, for finite repulsion, this amplitude is finite. Okay? And I get k equal 1. So you see that the perturbative formula that was that k is 1 over square root of u is completely wrong when k equal infinity. I would have found k equal 0. So it tells you that you cannot pass with bosons with point-like interaction, you cannot pass this magic value k equal 1. You can crank up the repulsion to infinity, but you will still be stuck to values of k between infinity and 1. We'll see how you can pass this magic value, but not by cranking up the interaction. Okay? Now I get something which is non-trivial, because now I can compute the single particle correlation function. So if I compute psi of x, psi dagger of 0 bosons, well, you cannot get it from the free fermion mapping. Well, actually, you can get it. There are tricks. People have developed techniques to compute this directly in the single particle language, but it's sophisticated tricks. I can tell you how it decays. It's 1 over x to the power 1 over 2k. So this is 1 over square root of x. So using the field theory and the relation between the exponents and the fact that I have this magic value, I can very easily obtain correlation functions that would have been otherwise extremely difficult to obtain directly or brutally, even using the exact mapping. Yeah.
So, I mean, we expect in principle the lesson delivered to only give results for long distances, well, for no energy.
Yeah.
But here we now see correspondence at all and energy for the Postgraduate. I mean, this is an exact.
No. So the mapping between the bosons and the free fermions is, of course, valid at all energies. These expressions here, they are still valid asymptotically. At short distance, you should compute the proper, you see that if I do x equals 0, this is nonsense. So I should compute here the density properly for free fermions, and then it's not exactly the form that is given by the field theory. At short distance, it has to be changed.
Okay, so this is not the
It's not exact. No, this is not the exact, so this is for, let's say, x large. Now, otherwise there is a complicated expression, but it's not going nicely as just 1 over x squared. You see, do x equals 0. You get the square of the density, or you get, if you subtract, you would get 0 or something like this, but certainly not a divergence when x goes to 0.
Yeah, sure, but it's not clear where this max was. This is still supposed to hold.
Okay, so that's a very good question. Where would you say we screw up with the field theory? So if I am very naive, I would say I screw up when I deviate significantly from the linear spectrum, which is here. And I will deviate significantly from the linear spectrum when I will reach energy where the curvature here is significant compared to the straight derivative of the energy. So I need energies which are of the order of EF. And essentially, it now depends on what is your chemical potential, but if I convert this into distance, it means it will fail when I look at things of the order of the distance between the particles, kf minus 1. So it's quite logical that the field theory will not be able to give you something which is valid at distance of, let's say, maybe less than 2 lattice spacing. And actually, if you do active comparisons, you will see that this is roughly correct. So you're absolutely right. At short distance, even with the mapping, it doesn't help the field theory. Now, from the mapping, you could compute the full correlation, not only from the density, but also if you work very hard and use either replicas or some determinantal representation, you could also compute this at all distances. Okay, so this is all what I wanted to say for the calculation of the Luttinger exponent. So now let me give you a couple of examples. Well, I can just maybe finish this bosonization and concept of Luttinger liquid by just mentioning one thing, which is on which I will not elaborate too much, which is the effect of finite temperature. So there are two ways you can do that. The first one, your Hamiltonian is a free bosonic field. So going to finite temperature means when I was telling you, you get a sum over Q and omega, 1 over omega square plus Q square, blah, 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 1 minus cosine QX plus omega tau. Well, the answer is go to Matsubara, and then the sum over omega becomes discrete frequencies, and then you have to do the corresponding sums, Q square, 1 minus cosine, QX plus omega n tau. And okay, you do your discrete sum and blah, blah, you get the results at finite temperature. One. So that's one method. The second method is to say the theory is conformally invariant. And if I am at finite temperature, I have a periodic function in time of size beta. So actually, I am not computing in a 2D plane, x tau. So this would be infinite temperature with tau axis and space axis. But I am computing on a torus. And now you do the conformal transformation to go from the torus to the plane, which is log. And you inject in the correlation function, and you get the same result than if you did the Matsubara sum, of course. That's, so it's your favorite choice. You use one or the other. You will find in Jérôme's note the conformal invariance. At the end of the chapter that I gave you, you have also the conformal method. You can do the direct calculation, at least for the simple correlation we use here. It's not much more complicated. So what is the result? The result is that the correlation function, let's say as a function of space, so whatever, O of x and let's say tau equals 0, well, they will start decaying as a power law, 1 over x to some exponent, and then at a certain distance x, which is of the order of beta, the inverse temperature, and you would say, but this is not a distance, you have to put the velocity in the proper way to get a distance. So beta is an energy, so an energy is time minus 1, so you have to introduce the velocity. Then this will decay exponentially with a correlation length psi thermic, and psi thermic is of course proportional to beta, but what is remarkable is that the coefficient of proportionality is not arbitrary. It's something which is very well fixed and which is directly connected not only to beta, but to k, the value of the exponent that you would have had at t equals 0. This was originally, I think, I don't know who is the first to derive this formula. There is something which is known as the Luc formula, where such relations were derived. And then, of course, after conformal invariance came, this is a sort of straightforward consequence of conformal invariance, which also tells you that if you do, for example, a simulation at finite temperature, from the exponential decay of the correlation, you can extract the Luttinger parameter. So that's another trick to extract the Luttinger parameter. Okay. It also tells you that if I have a quantum problem at finite temperature, it becomes a classical problem because the time direction disappears essentially. And therefore, you get the standard exponential decay that you have for a classical 1D problem at finite temperature. Yeah.
R is x as well, right?
Yeah, it's x. Yeah, it's a mistake on the slide. It's x. It's x. No, it's there is no time in this picture. Again, the time is limited of size beta. And if I go to very large distance, in any case, x squared plus tau squared is dominated by x.
Okay.
So I can just compute the correlation at tau equals 0, and it's essentially the same at large distance.
Correlations for fixed x and time correlations, like how?
You mean real time?
Real time, yes.
Then you need to do the analytic continuation from the Matsubara, and there are well-defined procedures to do this. So typically you replace tau by IT plus a regulation, plus a regularization. So there is an analytic formula, or you could do it in Fourier space. So you do first the Fourier transform, and then you have to replace omega n, the Matsubara frequency, actually I omega n, by omega plus I epsilon. And then you go back to real time, and you get the retarded correlation function. So computing a time-ordered correlation function in imaginary time brings you by analytic correlation, by analytic continuation, the retarded correlation function in real time. Okay? Yeah. Oh, there is no singular point. It's a smooth crossover. And that's just my inability to draw with PowerPoint. Essentially, the correlation function is something like a power law of 1 over hyperbolic sine of x divided by beta. So if x is small compared to beta, the hyperbolic sine is linear, and this gives a power law of x. And if the x is large compared to beta, the hyperbolic sign is essentially an exponential, and then you get the exponential. But there is no kink. You're absolutely correct. I should really draw a smooth function, but sorry, I'm not able to do it. Okay, so let me show you a couple of examples of experimental systems in which one can test for Luttinger liquids, and I take it as a kind of, let's say, internal break, because I won't justify many of the formula that I will show you, and I will present to you calculations on fermionic systems, for example, which I have not yet discussed, but I will discuss them in a moment. So probably one of the most ancient systems, which is 1D, is these so-called organic conductors, which are made of molecules which are stacks on the top of each other, and then the hopping between these plates, if you want, which are stacks on the top of each other, is much more easy in the direction perpendicular to the screen than it is if one electron needs to hop from one chain to the other. So we are in one of these cases where the T are extremely anisotropic that I was mentioning before, and so at intermediate temperature, these systems are very well described by a 1D theory, okay? And therefore, it's a Luttinger liquid, and if you compute their conductivity, and I won't do the calculation, well, lo and behold, you find that it's a power law of the frequency. And, you know, power laws everywhere, so this is what you expect. And here are measurements that were done in the group of George Gruner in Los Angeles. Martin Dressel and Leo De Giorgi were the people doing this essentially studies. And lo and behold, if you plot the frequency-dependent conductivity, it's indeed a power law over more than a decade, limited by another physical phenomenon which occurs at this frequency, and the bandwidth of the material here. We fall in the question you were asking, when should I stop trusting the field theory? Well, when you reach the end of the band, that's it. You cannot linearize the spectrum anymore. I think it was the first observation of this Tomonaga-Luttinger liquid behavior. Another class of system are carbon nanotubes. Here is a photograph of a carbon nanotube. Colors are, of course, completely false. They have been put by hand on 2 gold contacts. And, of course, a carbon nanotube. Now people would say a carbon nanotube is a wrapped-up graphene sheet, but it was carbon nanotubes occurred before, so it's a rolled-up graphite plane, or whatever you want to call it, or graphene sheet. And the dimensions are so small that, again, you get strong quantization around this direction. So these are very good one-dimensional system. And again, lo and behold, if you measure the conductance of this stuff as a function of the temperature, you get power laws. There are issues with this data that I don't want to discuss. And there are many others that I won't have time to discuss. Now, one system which has been extremely favorable to observe Tomonaga-Luttinger liquid and to observe, let's say, 1D system has recently been provided by cold atomic systems. So here, let me again do a poll. How many of you are familiar or reasonably familiar with cold atoms? Half of the room. Okay, so I give you my crash course on cold atoms, again, just like the crash course on Fermi liquids. And again, if you want a couple of references, there is a very nice review that was written by Emmanuel Bloch, Jean Dalibard, and Willis Verger, and a more recent one by the group of Tillman Esslinger. and we did some review for Les Houches, connecting the question of cold atoms with, of course, many of the question of strongly correlated material. So, in short, now people know that using lasers, you can not only trap atoms, but you can also cool atoms. If you think about it, it's not so trivial, because you would imagine that if you shine a laser on something, you warm it up. But actually, by using a battery of tricks, you can cool it. Here is a little image of a ball of sodium atoms which is trapped and which is fluorescing. So that's why you see it. They throw light and the light is re-emitted. Now, what is the interest in trapping atom in a trap of light? Well, the interest is that the atoms don't touch anything. And then it means that they can be in a box which doesn't exist. The reason is that if you have a box, the walls of the box, they are at room temperature. And if you want to cool what is inside, it better not touch the walls of the box, because the walls of the box are incredibly hot. It's like taking an ice cube and putting it in a frying pan. It's a disaster. So you don't want that, but if your ball of atom doesn't touch the wall of the box, needless to say, in the box you have to have an impeccable vacuum. I could ask the usual joke: what is the material which per gram costs the most? It's vacuum. If you want to make a good vacuum, it costs a lot of money, and per gram, it's really a lot of money. Okay, so this is a little picture of the speed that atoms have at various temperatures. In the room here, we are at 300 Kelvin. The speed is essentially the speed of sound. So an atom here in this gas is moving at 300 meters per second. Now you cool it. In condensed matter, you go typically to 1 Kelvin. If you work very hard, you can go to, 50 millikelvin or something like this. By that temperature, the speed of atoms is 1 meter per second. Still pretty fast. And now, with this technique of laser cooling, you can go down to the nanokelvin, 10 to the minus 9 Kelvin. So I want to emphasize, this is much colder than the vacuum of the universe, which is at temperature of order of kelvins. So these labs where there are cold atoms, and there is a fantastic lab around here at Lens in Florence, this is a high place of cold atoms, is or are the coldest place in the universe, literally. Okay? Temperatures of the order of the nanokelvin. When you reach these temperatures, the speed of an atom is less than the speed of a snail. It's 1 centimeter per second. But much better, the de Broglie wavelength, which is the wavelength which tells you at which distance you get quantum coherence, is now very large. Which means that in a solid, why do you get quantum effects? Because distance between particles is 1 angstrom. So at room temperature, 300 Kelvin, the de Broglie wavelength is larger than the distance between the particles. Coherence, let's say Pauli principle, and so on and so on and so forth. With cold atoms, you would get 1 atom every micron. So you need to cool down extremely strongly so that the de Broglie wavelength of the particle now reaches the micron, and you still get the same quantum effect. But except for that, it's the same physics. Okay? So in 1998, this was the Nobel Prize of Steve Chu, Claude Cohen-Tanuji, and Bill Phillips for the cooling. And then in 2001, Eric Cornell, Wolfgang Ketterle, and Carl Weyman showed in a very spectacular way that using this technique, you could obtain Bose-Einstein condensation with a gas of rubidium atom. So this was another Nobel Prize. Actually, it looks like this. And now it's even much more complicated in the experimental labs. And what is the interest for us? Well, the interest is that you can do literally virtual solids. Because if you can trap the atom, you can also create, very simply, you just send 2 lasers, this creates a standing wave, and you can create a periodic potential. And the atoms will like to be in the minima of this potential made of light. And then you get, in quantum mechanics, the possibility for the atoms to tunnel from one of these minima to the next minima. minimum, sorry. So you have realized, with light and atoms, a tight binding model of quantum particle moving on a lattice. It's not the periodic potential created by the positive ions in a solid. It's a very nice periodic potential, which is controllable. The height of the potential is totally controllable because you change the power in the lasers. So you can control at will the hopping of the atoms. And the atoms are neutral, so you're not polluted by long-range Coulomb forces or whatever. So all the nice models that I wrote, the Hubbard model and blah, 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 they become essentially exact with this type of systems. The atom being neutral, they only see each other if they are in the same well of the potential. There is a super weak van der Waals force here, but it's so small that even at the nanokelvin you can forget it. And so you have an interaction here if the atoms are in the same well. And the guys in quantum optics, they are extremely smart because not only you get this interaction, but they know how to tune it by putting a magnetic field and using something called a Feshbach resonance, so adjusting the energy level of the atoms, so that they can essentially vary this interaction between minus infinity and plus infinity, within reason. Okay? So this makes a fantastic tool for realizing fake solids in which you can control the tunneling and you can control the interaction. And the proposal was made by Peter Zoller in the end of the 20th century, let's say. And it took a little time, but then this was actively realized experimentally, and therefore you can use these objects as quantum simulators to simulate problems in quantum matters. And there is a very influential paper that was done by the Munich group. So Marcus Greiner, Tilman Esslinger, Ted Hensch, who got the Nobel Prize for other works he did on quantum optics, and Immanuel Bloch. And they showed very spectacularly that if you put bosons in a periodic potential, when the periodic potential was weak, you would get a Bose-Einstein condensate. This is the momentum distribution of the bosons. You see the huge peak at k equals 0. So most particles are in the condensate. And then if the periodic potential is large, well, the bosons, they repel. They prefer to sit like eggs in each minimum of the egg box. And essentially then having motion of the boson would cost a repulsion nu. This is what people call a Mott insulating state. And then you see that the big peak at k equals 0 has disappeared. The system is not a superfluid, it's an insulator. Okay? So this was a spectacular quantum phase transition that was demonstrated in this system. And here is the actual data. You see the peak at k equals 0, which disappears as the strength of the interaction. Actually, in the same paper, they also launched a complete line of investigation because they also said, but what happened if I change brutally the potential? And this was the start of many, many research on out of equilibrium quantum physics. And this is in the same paper. Because they could do it. In a solid, you cannot say, let me remove the periodic potential. You know, I zap all the ions in the solid like this. Here you do. You just switch off the laser. And then the periodic lattice disappears. So you are in the Mott insulating state, and you can instantly switch off the lattice, and then you should go back to something like this. Or what happens? So this is what prompted many, many studies on out of equilibrium physics. Okay, so as I said, it's a remarkable type of system because you get control on the interactions, you get control on the tunneling, you get control on the statistics because atoms can be either bosonic or fermionic. Helium-3 is essentially a fermion. Helium-4 is essentially a boson. Lithium-6 is essentially a fermion. Lithium-7, the isotope of lithium, is essentially a boson. Now, exercise, why is helium-4 a boson, helium-3 a fermion, and lithium-6 a fermion, and lithium-7 a boson? I want the answer by tomorrow. No, I'm joking. So this is an exercise. Think about it. Here is the momentum distribution for bosons. You see the peak at k equals 0 that develops, signaling the Bose-Einstein condensation. Here is the same experiment for fermions. Well, what do you expect? Free fermions. You have the Brillouin zone on a square lattice, on a cubic lattice. It's a square. And that's exactly what you see. N of k is flat here and drops, and it has a square form. There is not a single solid which has a square lattice. Everybody teaches you the Brillouin zone of a square lattice, but it doesn't exist. I mean, just here it exists. You can, of course, and that's the most important for what I'm going to say, and I'll stop here, you can control the dimensionality. Because if I make the laser here and here super powerful, I can completely prevent tunneling from here to here. So I can do 1D tubes. Or I could slice by putting only 2 lasers, I would do 2-dimensional systems. So you have a huge flexibility, and you can therefore use this system to do a certain number of things. So I think it's a good point to have the break. We'll stop here, and then I'll show you some of the experiments that were done right after the break. Okay. Because it gets very technical.
Yeah, this is the only like side note that I found.
It gets very technical very fast. Okay, so let me show you a couple of examples of essentially things one can do to compare with this Schlesinger liquid theory coming from cold atoms. So here is an experiment that was done in the group of Dev Weiss already a long time ago, 2004, where he realized many tubes. So here you see, so the tubes are in the intersection of various lasers, blah, blah, blah. And in this tube, he was able to control the strength of the interaction. So these are bosonic tubes, 1D bosonic tubes. And so they are narrow enough that the quantization is such that you can ignore all the higher bands. And essentially, he was able to control the interaction. And what he was able to measure by a devious method is essentially the, let's say, energy of the system. So the dash curve here is essentially the energy of a free bosonic bath, a free bosonic tube. And the straight line here would be the energy of a free fermionic tube, which corresponds to the total energy of the field Fermi-C. And you see for the particles that he has, as the function of the interaction that he has in the system, or this is the microscopic interaction, this is the interaction normalized to the kinetic energy, that essentially the experimental curve, let's say at the beginning is kind of maybe closer to the free bosons, but as the interaction becomes large, and it can become pretty large, it tends to the one of the free fermions. The red line, if I remember correctly, I should have rechecked, should be the Bethe-Ansatz calculation for the energy of the Lieb-Lininger model, and the data agrees pretty well with this calculation. So this is, if you want, a test, an experimental test of both the exact solution of the Lieb-Lininger model and from Bethe-Ansatz, and also the fact that the two limits correspond, of course, to nearly free bosons on one side, but also nearly free fermions on the other side. Shortly after, there was an experiment in the group of Immanuel Bloch, where he realizes also many tubes, and he measures by a technique that I don't want to discuss, which is called time of flight. He's measuring the n of k, the momentum distribution, again, the Fourier transform of the single particle correlation function for his tube. So this we computed, and so if the repulsion is super large, what we should see is a momentum distribution, which is a power law of x, which means a power law of k. And the power we did compute is 1 over 2 big K minus 1. So if K equal 1, the power should be minus 1/2. So if this experiment was in agreement with what we all discussed so far, what Immanuel and his group should see is a nice power law in the n of K diverging as K goes to 0 as 1 over square root of K. So here is the experimental result. This is the n of K. It's called P here. So P going to 0 is here. This is on logarithmic scale. and n is here. Okay. Do you have comments on this data?
It's surprising that the short wavelength result is, sorry, that the long wavelength result is not so close to the.
Okay, you can say I cannot go maybe to too long wavelengths because, well, of the size of the system. Fine. Yeah, so the first comment is that it doesn't really look very much like a very nice Paolo. So you could say, did they do something wrong? And no, they didn't do something wrong, but I lied to you because the experiment, actually, you need to trap the atoms. And the way they trapped it at the time is with lights, of course, as I said, but with a shape of the light, which is naturally obtained when you send lasers to the center. And it's like having a chemical potential that is growing as R squared from the center of the trap. So this system is not homogeneous. When we do calculation, we are used to box, maybe. We are used to periodic boundary condition, but not to a chemical potential that is growing parabolically in the system. So along the tube, there is a chemical potential which is varying as a parabola. So the density at the center of the tube is not the density far away from the center of the tube. But worse, it's also in the two transverse direction. So this tube doesn't have the same density than this tube, which doesn't have the same density than this tube. And that makes it super complicated now to compare with theories which implicitly assumes that the system is homogeneous. So there are ways to take this into account, and that's why you see theoretical lines here which go through the data, which are based on the free fermion description, using then the fact that the density has to be taken into account as varying among the tubes. So the experiment works very well with the theory, but they need to do more efforts if they want to directly read Paolo's out of the experiment because of the trap. So this is a super essential or inessential complication. Essential experimentally, it's a nuisance in a way most of the time theoretically, and I think Jérôme will tell you cases where it's not a nuisance, where it's something super interesting. But you have to face the fact that there is a potential which is varying as over R squared. So you get no homogeneous phase if you're in this situation. And for most experiments, it's a disaster. So now several experimental groups in cold atoms have started to work on box-like potentials, which are much more difficult to engineer, but which are, of course, much better if you want to do direct comparison with theory without needing a theorist to solve the problem on a computer, then convolve with all the complication of the varying density, and then making facial recognition with the experimental data. So just to mention that this is a complication. Here is another test of Tomonaga-Luttinger liquid, which was done in the group of Jörg Schmidtmeyer in Vienna, and the theory was done by the late Adilet Imambekov, Vladimir Gritsev, and Eugene Demler. So again, I don't want to go too much in details, but the good thing about this experiment is that there are only two tubes. So already you get rid of a good part of the trapping effects. There is still the trap along the tubes, so the density is still not the same from point to point of the tube, but at least there are only two of them. And essentially the idea is that they take a single tube, they split it in two electromagnetically, and then they let the two tubes fall, and when they fall they expand and they interfere, because this is atoms, but this is also waves. So they interfere, and then they measure the interference pattern by shining light on it. And what is measured, if they integrate this interference pattern over a window of size L, is essentially the integral of the single particle correlation function. So if you were at t equals 0, this would be a Paolo. At finite temperature, because unfortunately, even if it's nanokelvin, it's still finite temperatures. At finite temperature, this decays exponentially, but with a characteristic length that you can compute, and so you can still test the prediction of what I would call finite temperature Tomonaga-Luttinger liquid, or you get exponential decay. And the data is in very good agreement without adjustable parameter with what you would expect. Limitation of this experiment is that for the moment, but they are working on it, for the moment they are limited to extremely small repulsion between the particles. So the K is super large, which, you know, for the single particle correlation is not a problem. It means that there is essentially no trace of Luttinger liquid physics in the density-density correlation. I mean, if you think about 1 over x to power 80, you move by 2 lattice spacing and it's gone. So it would be interesting to go to stronger repulsion. That I will show you later because I've not talked yet about this. Okay, so this is a couple of examples of what we can do with bosonization. And now I would like to move, because, okay, we've exhausted a little bit the pleasures of bosons. And there was a question the other day on, is it limited to bosons? Can we do fermions, spins, perhaps even particle with fractional statistics? So let's start little by little, and let's do spins. So let's do 3 spin systems. Okay. So spin systems, typically, as I said, the Hamiltonian that people look at is the so-called XXZ Hamiltonian. So let me write, again, it's not a mandatory. You can modify your Hamiltonian as you like. So let me write this one. I and j are nearest neighbors. So if you want, j is equal to I plus 1. And then I put a different jz, which is, again, szy, SZJ, and I could even put a magnetic field, which is the sum over J of SZJ. And now I would like to know, can I bosonize this thing? So do I have to work very hard? I pretend that I have 0 work to do. I like when I don't have work to do. What are spins? Spins are hardcore bosons. Spin 1/2. If I take a spin 1/2, the Hilbert space consists in 2 states, down and up. I have the operator SZ, I have the operator S plus, I have the operator S minus. If I have these 3 operators, I'm fixed. Now, what is a hardcore boson? It's something which has 2 states in the Hilbert space, 0 and 1. If SZ is equal to minus 1/2, I could say that the number of bosons is 0. If SZ is equal to plus 1/2, I could say that the number of bosons is 1. So this strongly suggests that I will write that SZ is the number of bosons on side J minus 1/2. I can say I can create an operator, a boson on side 0, on state 0, and then it becomes a state with 1 boson. You immediately see that this is the same thing than the operator S plus acting on down, which gives you up. Now, normally with bosons, you could do it twice or 3 times. But if they have a hardcore repulsion, you can't. So by putting a hardcore repulsion, you cut the Hilbert space of bosons to only 2 states. And then it's really equivalent to spin 1/2. If you add regular bosons, of course, the Hilbert space is infinite on each side, and then it's not equivalent to spin 1/2. So there is a perfect mapping. So what should I do to check if my mapping is correct? Yeah, you should check the commutation relation between the spins. So you should check that whatever, S alpha, S beta is equal to I S gamma, where you get all the permutation, you get all the permutation that are possible. Did I put an I, which is not there? Forgot if there should be an I. S plus, S minus is SZ, so there is no I. Okay, so you should check the commutation relation. So I let you do it as an exercise. It's not very complicated. And you will find that the commutation relations are perfectly respected. Spin on two different sides, they commute. Bosons on two different sides, they commute. So you just need to check on the simple site. And if you want to identify, you just work it out for all the states in the Hilbert space, which is easy because there are only two states. So there is an exact representation. I can re-represent this Hamiltonian in terms of my hardcore bosons. So I could write that this is J, let's call it JXY, just to keep it simple. JXY, sum over, let's call it little j. The operator, okay, so SX plus SY is S plus S minus, J plus 1, plus S minus S plus, J plus 1, plus JZ, sum over SZ, SZJ, SZJ plus 1, minus H, sum over J, SZJ. Now, I just use my mapping, and I say I get JXY, sum over J, S plus is B dagger J, S minus is BJ plus 1, plus BJ, B dagger J plus 1, plus JZ, sum over J, NJ minus 1/2 times NJ plus 1 minus 1/2, minus H, sum over J, of NJ minus 1. So what do I have? What I have here, sorry, let me put it maybe more below. So what do I have? I have a system of bosons, hardcore bosons, which are hopping on a lattice. This is a tight binding model of bosons, which are jumping on a lattice. These bosons have a nearest neighbor repulsion and a chemical potential. So I can map exactly my spin problem onto a problem of interacting bosons, so with the nearest neighbor repulsion. Of course, don't forget they are hardcore, so if you want, you could say also put an on-site repulsion, which I let go to infinity, so it's your choice. You could also say there is also plus U over 2, sum over J, NJ minus 1, but this is infinite, otherwise I don't get the Hilbert space. And therefore, I can, every problem I know how to solve with bosons, I know how to solve for spins. Now, it's a little bit unpleasant to have here the hopping, which is positive. For an antiferromagnetic system, J is positive. So I will do a transformation to bring back the more conventional tight binding model where you would like the minimum of energy to be at Q equals 0. So let me do a gauge transformation. I will say that Bj is for J, B tilde, and I'll get rid of the tilde instantly after Bj. So I put a phase of pi on one boson on every two sides. And then it's very easy to see that my Hamiltonian becomes minus JXY, sum over J, B dagger J, Bj plus 1 plus Hermitian conjugate, plus J sum over J. And of course, the density is the square is B dagger B, so the minus 1 goes away. So this is unchanged. So this should be tilde, of course, everywhere. And tilde J minus 1/2, and tilde J minus 1/2, minus H sum over J, and tilde J minus 1/2, plus hardcore. Okay. And now you know why people don't like this mapping. I mean, should I like this mapping? Is it a useful mapping in 2D or in 3D? Wow, it's a pretty nasty interacting problem to solve because the repulsion here is infinite. So in 2D or 3D, it's a mapping you can do. You can do it in 1D, in 2D, 3D, it doesn't matter. But you have to solve a problem of infinitely repulsive bosons, which is a highly non-trivial problem to solve. If U and JZ are small, you could say I expand or I do mean field or whatever. But if U is infinite, it's a little bit nasty. So usually people prefer to use other mappings. But for example, in 1D, you can map spins onto fermions by a complicated transformation, which is called the Jordan-Wigner transformation. But here I don't want to do that. I stick with my bosons. So here I have bosons with a kinetic energy. Now, if I go to Fourier space, I have bosons with a certain kinetic energy, which is sum over k of epsilon k, b dagger k, bk, and epsilon k is minus 2jxy cosine k. So I get the standard dispersion relation of particles on the lattice. Is there something I could do about it to solve this problem by using my field theory, for example? Actually, we solve this problem, this plus this. Tonks limit. I just replace this part of the Hamiltonian by the field theory with k equal 1. Because I know if the bosons cannot cross, they can behave as free fermions, and I will do all the things I did before. So I'm claiming that my spin Hamiltonian, H spin, is directly mappable onto my favorite field theory, 1 over blah, 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 uk pi square plus u over k grad phi square. And I will automatically incorporate, and then I have a term which I need to deal with, which I didn't encounter before, which is nj minus 1/2 times nj plus 1 minus 1/2. Okay, chemical potential I'll remove because I can fix the number of particles. I can fix the thing. So in a way, this part is my bosons on the lattice plus the infinite repulsion. And if I say I have infinite repulsion, I know I should take k equal 1. This is infinite repulsion. What is the velocity u? Well, it's the velocity of the fermions of the corresponding theory. So the velocity u is d epsilon k dk taken at k equal kf. Now, what is kf? Well, kf will depend on how many bosons I have in my system. If, for example, I have no magnetic field, then the average magnetization along Z has to be 0, which means the average of the number of bosons minus 1/2 is equal to 0, which means the average number of bosons is 1/2. So in that case, I would have my band of bosons, of fermions, or whatever you want to call it, which would be half field, and kf is pi over 2. So I can compute the velocity perfectly. Yep.
Do you assume that JZ is small?
For the moment, yes. So I don't want to consider JZ for the moment.
And if the argument like small, so it does not modify the low energy theory,
Yeah.
but it's really what you're doing.
Yeah. So for the moment, let me say I look at a model where JZ is 0. I'll write it, but I ignore it for the moment. And then what I will do in a second is just to say I'll start from this field theory where JZ is equal to 0, which I know to be exact, essentially, or essentially exact. And then I will do what I did for the bosons. I will use the bosonization formula to write the bosonized form of this term. And this will modify this field theory. And again, I will see what is the shape of this field theory. If I am lucky, it will be perfectly quadratic. And then I know that I modify the parameter u and k, and I know I should find a better way to find the modification of the parameters u and k than do it perturbatively. But I can again use the same tricks than I did before. But as you will see, we will be a little bit unlucky, and the theory is not strictly quadratic. So that's a price we will have to pay. So is it clear, the idea here? I just say my spins are hardcore bosons. So I can use completely the formulas that I had for bosonizing the bosons up to now. Yeah. So here, indeed, I assume that I'm interested in large distance, long wavelengths, and whatever, much larger than the lattice spacing. So in a way, I'm taking the continuous limit. So you're right. In a way, you see that if I write it in k-space, continuum limit says, or discrete limit says only that I limited the value of k to minus pi over a and pi over a, while if I was strictly in the continuum, I would get a parabola which extends to k equal infinity. But if I say my chemical potential is here, at long wavelengths, it will not make much of a difference. You're absolutely correct. I implicitly assumed that I could take a kind of continuum limit, because here my band is limited between minus pi over a, pi over a. But again, if I look at small energies, meaning energies which are within a sort of box here, I cannot really make the difference. But you're absolutely correct. Okay, why am I presenting this mapping? Because now I have a very simple mapping of my bosons. S plus, I map on B dagger, and B dagger is minus 1 to the j times B tilde dagger on side. And B tilde dagger on side j is my psi before. So this is something which is minus 1 to the j times exponential of I theta times rho 0 to the 1/2 plus exponential of I 2 pi rho 0 x minus 2 phi. Now I put the next harmonic times exponential of I theta, and I think there is a minus I theta if I put, doesn't matter here. Okay. SZ minus SZ is NJ minus 1/2, and J minus 1/2, this is NJ0, this is the average value, and therefore this is minus 1 over pi grad phi. Sorry, there is again, no, sorry, on this one there is no modification. So this is minus pi grad phi plus exponential of I 2 pi rho 0 x minus 2 phi plus Hermitian conjugate. So I have directly the bosonization formula for the spins. So let me rewrite them a little bit in a more elegant way by remembering that kf is pi over 2. So if I use kf equal pi over 2, 2kf is pi, and exponential of I pi x is minus 1 to the x. Okay? So what I get here is that S plus is minus 1, S plus j, is minus 1 to the power j, some amplitude which I don't care, exponential of minus I theta at point rj. And then I get a second term here, where the part here, minus 1 to the j, cancels with the oscillation which is here. And I just get something which is exponential of minus I theta of rj, exponential of I 2 phi, with probably a minus sign with what I wrote, rj. Now, I get another term, which is szj is equal to minus 1 over pi grad phi at point rj, plus minus 1 to the power j, and then I will get exponential of minus I 2 phi of rj plus Hermitian conjugate. So here is the bosonization formula that I have for my spins as a function of the field phi and theta, written, I would say, without much effort, directly from the representation of the bosons. So you see that this representation has two types of terms. In each type of term, I have a part which is oscillating minus 1 to the j from side to side. This is true in S plus. Of course, S minus is the Hermitian conjugate. And this is also true in SZ. So this is the just a second. This is the anti-ferromagnetic part. This is the part that when I move by one lattice spacing will change sign. This is what I would expect in an antiferromagnet. But there is a second part, which is a smooth part, which is varying slowly at the scale of the lattice. And it also says that there are ferromagnetic fluctuations which are propagating or which are moving from one side to the lattice to the next. So I will have these two components, and you see that these two components are controlled by different operators. So the anti-ferromagnetic part will decay in a certain way, and the ferromagnetic part will decay in a different way. Yeah, so there was a question. Yeah.
I would like to know if this mapping remains the same if JZ is not.
So for the moment, let me, as I said, take JZ equals 0. And as we did for the bosons, the mapping so the mapping between spin and boson is valid regardless of what JZ is. It's just the mapping on the Hilbert space of the spin problem and the spin 1/2 problem and the boson with a hardcore constraint. So this is valid, whatever. You can take any lattice, any J, whatever. You can do the mapping. Then this representation is the bosonized version, which already incorporates the hardcore constraint. And of course, what the resulting Hamiltonian will be will depend on the strength of JZ, and that we still have to work it out. Okay.
Sorry, could you please explain the SZ mapping? So why is the 1/2 pi J, is it not just the density and J, so it's not B dagger B, effectively?
Yes, it is. But I have to subtract 1/2 if I want that SZ is minus 1/2 when I have 0 boson, and it's plus 1/2 when I get 1 boson. And it just happened that this value is the average density of the corresponding bosons. So that's why there is no rho 0 term here.
Okay, but when did the grad phi appear? It is just by B dagger B, it's never done with the
No, so the grad phi appears because my density, when I bosonize, the formula for the bosonized density has a grad phi.
That's clear, but we didn't write the grad phi for the B dagger part.
No, but look, let me go back to the bosonization formulas for the density. So I have this bosonization formula for the density, which is that the density is essentially rho 0, I take the term P equals 0, rho 0 minus 1/pi grad phi, plus oscillating terms. And that's the formula I used. And I also used that rho 0 is 1/2. So this term goes away. So when you bosonize the density, you should then just take the bosonized formula for B dagger, multiply by the bosonized formula by B, and recover this formula. You can do that, but it's an extremely complicated task because you put the operator rigorously at the same point. And then you have a lot of short distance problems that will happen because if you look at the notes of Jérôme, you have to regularize your theory properly at short distance. So recovering this formula by taking the B dagger and B, you have to be really careful when you bring the two operators at the same point. So that's why there is one bosonization formula for the density and one bosonization formula for the single particle operator. Because implicitly, when you will compute the correlation of this object, they will be separated space-time.
But in the harmonic, you omitted the grad phi or the rho 0. Like if you go back to the formula, like for SZ,
Yes?
the harmonic should be multiplied by the grad phi as well.
Oh, no. So SZ is not multiplied by anything because the transformation multiplies B, but it multiplies also B dagger. This one.
Without the J, so where you have the minus 1/pi grad phi plus the harmonic, should the harmonic be multiplied by something as well?
Oh, then again, the harmonic, I will say I only retain the rho 0, which is the dominant part. So you're right. So okay. And grad phi will be a higher power, so it's a less relevant operator. So I keep again the dominant operator. So you're right, there will be also a term grad phi exponential of phi blah blah blah, but because of the gradient phi, it will decay faster, and therefore I throw it away. But I should worry about this term potentially. So I only wrote the dominant terms, the dominant term that does not oscillate, and the dominant term that oscillates, for which I just keep rho 0. So you're perfectly correct. Okay. So are there other questions on this formula? Yep. So here, JXY is restricted to nearest neighbor. So of course, you could consider extensions of this, where JXY would couple I and I plus 2, or I and I plus 3, and so on. So then I will modify this part. So epsilon k will now be modified by adding the, so this cosine k comes from the fact that it only couples nearest neighbor. If I go to second nearest neighbor, I would have cosine 2k. And I would say as long as the dispersion around pi over 2 remains reasonably linearizable, it probably doesn't change much. If the range in hopping becomes too long, infinite range or whatever, or if the dispersion here has a singularity, then I have to reevaluate what I'm saying, because I need the dispersion to be linear around the Fermi, or around KF. So one can extend this theory to longer range JXY, but one has to be careful that at the end, I can sort of have a linear spectrum around here, this point, and this point. Otherwise, I have to find another method. Okay? Okay. So, now we are nearly there. So I can do two things. I can look on how the Hamiltonian is modified, or I can compute the correlation functions. So let me first assume the Hamiltonian would remain, at the end of the day, totally quadratic, but maybe with a new u and a new k. Just, let me compute the correlations. So if I compute the correlations, let's start with SZ. SZ Rj, SZ0. Then again, I get two parts. I get the part which is 1 over pi square grad phi, and then I will get one part which is -1 to the power Rj, and then I will have the average of exponential of I2 phi of Rj, exponential of minus I2 phi of 0. And this will give me, again, something which decays as 1 over R square, x square, let's say. Blah, blah. I don't repeat the calculation. And then I would get -1 to the x, and this would decay as 1 over x to the power 2k. Okay? That's the same calculation we did for the density of bosons. I'm not saying the k is, now k is whatever it is. Let me do it for S plus, S minus. So for S plus, S minus, the oscillating term is just the first one. So the oscillating term would give -1 to the power x, 1 over x to the power, essentially 1 over 2k. And then I have a new correlation I never computed before, which is a mixture of this and this. So I let you look at the notes and whatever, and trust me on the result. This would decay as 1 over x. So the theta part gives you a decay which is 1 over 2k, and the phi part gives you an additional part in the exponent, which is plus 2k. It's quite reasonable, actually, at the end, if you look at the result. And there are angular factors that I don't want to discuss. Okay. Now, what does it mean? It means that if I look with these formulas at how the spins are correlated on my chain, I would find that the projection of the spin in the plane has one antiferromagnetic component whose correlations decay, essentially given by this part. It has also a ferromagnetic part that I won't draw on the thing, which decays much faster. Well, it's reasonable. No, I started from an antiferromagnetic coupling. I expect the ferromagnetic part to decay super fast. And you see it here. Again, I do all this assuming that at the end of the day, when I will have included my JZ, my final Hamiltonian will again be a Luttinger liquid Hamiltonian with a modified U and K. Because I remind you that if JZ is equal to 0, K equal 1. I know K if JZ is equal to 0. So let's assume I get a new K. K prime or K, whatever, K prime, say. On the other hand, if I look at SZ, then SZ, it's the same. I get an antiferromagnetic part of the fluctuations that is decaying as this, and I get a ferromagnetic part that is decaying with a universal power of 2. And again, if JZ equals 0, that's it. I don't need to do more than that. So if JZ equals 0, K equal 1, and so I can say S plus, S minus is oscillating as minus 1 to the J 1 over square root of x, and a uniform part, which is, and now I will probably 1/2 plus 2, this is 5/2, no? See, this complicated thing one needs a computer and a Monte Carlo program to do, which is, so SZ, x, and 0. This is minus 1 to the J with a power 2, so this decay as 1 over x square, and then I have a uniform part, which is 1 over x square. So are you shocked to see this correlation? By the way, I recommend trying to compute that directly. For the XY model, it's not so easy.
So it should be x, sorry, on the 0.
Oh yeah, x. Absolutely. So congratulations, we solved the the XX model, the model for which Z is equal to 0. So this is JZ equals 0. It's highly non-trivial to solve this model for JZ equals 0. For the professionals of the field, this model maps onto free fermions. Haha. But not the spin operators. Yes. And you recognize, again, SZ is the free fermion decay of the density-density correlation. 1 over x squared, 1 over x squared, and this is the cosine 2kf. When kf is equal to pi over 2, this is minus 1 to the j. But the S plus, S minus, oh no, it's not C dagger for the free fermions. There is a string operator, a highly non-local operator, which comes from the Jordan-Wigner transformation, mapping the spins to fermions. And that's a nightmare. It's a Fredholm determinant. It's an horror to compute. It can be done. Here, the field theory gives you directly the S plus, S minus correlation, because you know that K equal 1. So bing, bing, you just put the exponent. Okay. Now, we need now to see what happens with JZ different from 0. And I hope that I will find the quadratic theory. Otherwise, I'm dead. So let's try to do it. Yeah?
Ask about the magnetic field.
Yes.
Because you're now assuming half filling, which and you're at
Yeah.
a very specific point where these e to the 2 by row factors become
Yes.
free.
Yes. So if I am not...
This is stable again.
Yeah. So you're absolutely correct. So what will happen if I have a magnetic field? Well, I can do it two ways. I could add the corresponding term to the Hamiltonian and see how the Hamiltonian is modified. Or I could say at the end, the only thing that the magnetic field will do is to modify SZ. If I work with a fixed magnetic field, at the end I will get a certain average of SZ. It's not 0 anymore. It's whatever, 1/2, 3/4, blah, blah. So if I change SZ, I change KF. And then I just change 2 pi rho 0 here to put the actual value of SZ. So I don't have to change anything in these formulas. I just take these formulas as they are, but except to put rho 0 equal 1/2, I put rho 0 equal whatever it is. Now, instead of having -1 to the j, I will get this complex factor oscillating, and I just do like I did with bosons. I will get something like cosine 2 pi rho 0 multiplied by a power law and blah, blah, blah. And I might have to worry about the plus and the minus, but you can do the calculation exactly in the same way. So you don't have anything to change. One thing which might change is the value of k and u. And in general, they will change because u, it's obvious. If I shift here kf, I change the velocity. And k, potentially, can depend on the magnetic field. So I would have, again, to use a trick, or same type of trick, to recompute what the value of k should be in presence of the magnetic field. For my boson theory, it's clear. K stays 1 if Jz is equal to 0, because it's just shifting the chemical potential. So for Jz equals 0, K is always 1, and the magnetic field is just changing U, and you just have to change this rho 0 to reflect the correct magnetization. Now, how to compute the magnetization for a fixed magnetic field? This is, in general, a complicated question. For that, you need to solve the microscopic problem. If you ask me to plot the magnetization curve as a function of the magnetic field, it's a non-trivial issue. But if I know the curve m of h, if I know m, I just need to put m minus 1/2 here in the thing. So you can incorporate the magnetic field. I will show you how you can compute m of h in a second. Okay. Yep. Mm-hmm. Yeah. This one? This one? Yeah. If I put an anisotropy between XX and YY. Yes. So again, you can do it. So I could write it in two ways. Let's assume these coefficients are different. I get JX and JY. I could write the sum and the difference. So I will have a part which is the same than I've written here. And then I will have a second part where I would get a minus sign between the two. And then the same way that I'm going to treat JZ by the bosonized version, I would have to bosonize SX, SX minus SY, SY, and see what consequence it would have on the Hamiltonian. So we come back on this probably tomorrow. For the moment, I'm assuming that these two coefficients are equal. But you can potentially assume they are different, and then you will have to treat an additional term in the Hamiltonian that corresponds to SX, SX minus SY, SY. And, so again, the Zeeman effect, that was the same question, which is I can take it into account two ways. The first way is to say the consequence will be to change the average magnetization along Z. And then the only thing I need to do is then to replace rho 0 here by magnetization. Rho 0 is essentially the magnetization. And so once I've done that, I can use the same bosonization formula. One thing I would need to know is what is the value of K, the parameter, in presence of the magnetic field. So that is, in general, not a trivial question. Okay, let's finish with the calculation of the JZ term, because everything will be nice. I'm sure the Hamiltonian will be quadratic, and we will be super happy. You know, it's like any fairy tale. So I write the sum over J of Nj minus 1/2 times Nj plus 1 minus 1/2. So Nj is rho 0, which goes away. So this is minus 1 over pi grad phi plus minus 1 to the j. Let's say exponential of I 2 phi plus Hermitian conjugate. And then here I get again minus 1 over pi grad phi. So this is at side j. This is at side j plus 1. then I get -1 to the j plus 1, and I get exponential of I2 phi at psi j plus 1 plus Hermitian conjugate. Okay. Of course, I will immediately replace the discrete sum by integrals because I'm taking indeed the continuum limit. And now let's see. Phi is a smooth field, which means when I move by one lattice site, it has essentially the same value up to small gradient terms. So the product phi j plus 1 is essentially phi j square up to gradients. So the first term is essentially the sum over dx of 1 over pi square, product of this. This is grad phi x, if you want, square, plus gradients. Okay? So far so good. It modifies the quadratic part of the Hamiltonian. So it will modify k and u. Now I have cross terms, this one and this one. But this one oscillates super fast. So when I go to the continuum limit, phew, goes away. Same thing for this one times this one. Unfortunately, I have also to do this one times this one. And then the -1 to the j goes away. So this term is not oscillating at all. And I have to keep it. And so I have to keep a term which is minus sum over dx, because of the 1 here, of exponential of I2 phi, exponential of I2 phi, which is exponential of I4 phi, essentially. So at the end, I will have a cosine of 4 phi of x. And now I have a new Hamiltonian to consider. So now my full Hamiltonian is something that was, whatever, 1 over 2 pi u pi square, because k equal 1 here, plus u grad phi square. Then I get something which is plus jz sum over dx, this is pi square here, grad phi square. So this part is super okay, but then I have minus jz sum over dx cosine 4 phi. So this is okay. This is 1 over 2 pi times u prime k prime pi square plus u prime over k prime grad phi square, where now I could say that u prime k prime is equal to u, and u prime over k prime is equal to u plus jz over pi square, perturbatively, but then I have minus jz sum over dx of cosine 4 phi. So my Hamiltonian is not quadratic, and now I don't know how to compute the correlation functions. So tomorrow, so this Hamiltonian has a name. It's called the Sine-Gordon Hamiltonian. The first part is sometimes known as the Klein-Gordon Hamiltonian, and some smart high-energy physicists obviously thought that replacing the name of Mr. Klein by sine would be a fun pun of the world. So this becomes the Sine-Gordon Hamiltonian when there is, in addition, this term. But you see that now we're screwed, because now I don't know how to compute my correlation functions, and I have to deal with this Hamiltonian, which is more complicated. Hopefully, we will find a procedure, which will be an RG procedure, to get rid of this cosine if we can, and find new physics out of it. So tomorrow, we'll deal with the Sine-Gordon Hamiltonian. You see that this is a super important Hamiltonian. It comes in spin chains, but it comes also on bosons on the lattice, of course, because they are equivalent. And actually, it's also Berezinski-Kostelis-Thouless transition. This pops up all over the place. So to finish, in physics, you have two types of Hamiltonians. Either you're non-periodic in the field, and then the only thing you know how to treat are harmonic oscillators. That's the first part. Okay? Beyond that, You do perturbation, you do whatever, or you do an exact solution, fine. But otherwise, we always deal with quadratic Hamiltonians. If you have periodicity in the field, well, how do you put a periodic term? Well, the first periodic term in your life is a cosine. So, in a way, this is the first and simplest, this is the Drosophila, or the Ising model, or whatever you want to call it, of systems where you will have to worry about the periodicity of the field. And therefore, like the Ising model, like the Drosophila, this is a super important Hamiltonian that will control zillions of physical phenomena. So tomorrow we'll wipe out Sine-Gordon Hamiltonian and find what is the physics and whether these correlations that I computed for you here, which I gave you somewhere there with the values of k, are correct. I have an exercise for you, and I'll stop on this. Let's imagine I want to solve the model with Jz equal Jxy. The Heisenberg Hamiltonian, the perfectly symmetric, rotationally symmetric Hamiltonian. Without solving the model, do you think that this could work with a quadratic Hamiltonian? And if yes, what is the value of k? So I let you this, and we stop here for today.